Welcome to the lecture accompanying Chapter 1 of The Fundamentals of the Cosmic Perspective by Bennett. In this chapter, named A Modern View of the Universe, we're going to introduce the ideas that we will see throughout the semester. All right, let's get to it. We're going to start with an iconic image taken from the Hubble Space Telescope, a telescope that is orbiting our planet. And in this image, we see that the sky is full of galaxies. This is one tiny portion of the sky. Imagine holding your arm or your hand at arm's length and looking at just a little portion of your fingernail. And then if you zoomed in on that little portion, it would be full of this many galaxies. And it just is a testament to the fact that there are hundreds of billions of galaxies in the universe. And every one of these disk-like structures, known as a galaxy, that I'm circling here in the picture, itself contains hundreds of billions of stars. These are unbelievably large numbers. So our goal for learning is, what is our place in the universe? Where are we? And as I was just hinting at, how big is the universe? This is, of course, Chapter 1, or Section 1.1, the scale of the universe. So we can take a zoom approach. So we can start from Earth and we can continue to zoom out. All right? So here we are on Earth, our planet, our island of life in a vast open solar system. And of course, then in that solar system itself is part of something larger. But let's take a look at that solar system to begin. So here we are, the third planet from the sun, and here the planets are not spaced to scale. All right. In fact, the spacing between the planets is very dramatic. Okay. Or let me describe it this way. Actually, so here the scale. There's two separate scales, I should say. So if you look, each planet is just a little dot, and we're zoomed in on their relative size. So Earth is, you can see, just a small circle compared to Jupiter or Saturn. Excuse me. And because those planets, like Jupiter and Saturn, are gas planets. They're much bigger than Earth. But the spacing is a separate scale. So we can see that the three rocky planets, that's Mercury, Venus, and Earth, right, our home, that those three rocky planets are all rather close to the sun. But as we move further out, the distance between planets becomes much more dramatic. We can see the spacing between the planets is quite a bit. There's vast distances. We're talking about years of travel at our current speed of spacecraft to go from planet to planet. You know, maybe only a year and a half to get to Mars because that's only this distance here, but much further to get to the more distant planets and the moons around Saturn and Jupiter. But our solar system is just one little tiny speck in one arm of a vast galaxy. This galaxy has hundreds of billions of stars, about 100 billion stars like ours, each of which has its own solar system, or most at least, to have its own solar system and its own system of planets circling around it. Furthermore, our galaxy is part of a local group of galaxies. This is Andromeda, our big neighboring galaxy, which we will eventually crash into in billions of years. And this cluster of galaxies kind of moves together, but this cluster of galaxies is just one small part of a supercluster. And that supercluster is just one part of the entire universe. This big network of superclusters, like this thick section here, or if we zoom back in, this section of galaxies here, this is composed of hundreds, even thousands of individual galaxies. And the overall system of the universe is this tendril, this almost neural network of galaxies. All right? It's unbelievable. So let's define some terms. I'm just going to go through these quickly. A star is a large glowing ball of gas that generates heat and light through nuclear fusion. Not fission, fusion. Okay? Our sun is a star. It's a pretty average-sized star. Planets, like Earth, are moderately large objects that orbit a star. They shine by reflecting light. They don't produce their own light. They may be rocky, icy, or gaseous. So we kind of have a few key categories. Mars, for example, is rocky. Neptune is a gas planet. Okay? Furthermore, there's moons. This is an object that orbits a planet. So a planet orbits a star and a moon orbits a planet. Here's Ganymede, the largest moon in the solar system, which orbits Jupiter. Ganymede is actually bigger than Mercury, so it's a moon that's bigger than a planet. So moons aren't defined by size, but just by what they orbit. We, of course, have one moon. An asteroid is a relatively small and rocky object that orbits a star. So what defines an asteroid compared to a planet is size. Asteroids are small, planets are large. In between are things that are called planetoids, like Pluto, okay, or Ceres. These are basically large asteroids that are more spherical, but still haven't reached the classification of planet. And we'll talk more about what that classification is. But many asteroids are just a few tens of kilometers across. This one here we can see. So maybe the size of a city, and they kind of have a shape that maybe looks like a potato or something. They're not spherical. They never have been crushed into a sphere by the forces of gravity. Then there's a comet. So what's different about a comet? Because this is a relatively small and icy object that orbits a star. Well, if you look back, asteroids are rocky, comets are icy. That is the only difference, okay? They're both too small to be planets, okay? But they are defined by their composition. Asteroids are rocky, comets are icy, all right? And there's some kind of important ideas about what that means. Why do comets melt and have tails when they come close to the sun? You know, where do we see asteroids? Where do we see comets in the solar system? So these are all the ideas we'll discuss in detail in later chapters. A solar system is a star and all the material that orbits it, including its planets and moon. So a solar system is defined by a star. Everything that orbits a star only makes up less than 5% of the total matter of the solar system. So you can see this picture here makes the sun look small, right? Like Jupiter looks huge compared to the sun. But of course that's inaccurate. This picture just it doesn't want the sun to take up the whole diagram. In fact, the sun is, again, over 95% of the matter of the solar system. Everything, including big planets like Jupiter and Saturn, and the much smaller rocky planets like the one we live on, are just leftovers. They're just little remnants that are left over from the formation of the solar system that formed the star, in our case, the sun. All right? And we'll talk about the details of the solar system, the very edge of the solar system, and so on in later chapters. Moving on, more terms, we have a nebula. This is an interstellar cloud of gas and or dust. So nebulae are much bigger than solar systems. So you can see this nebula is vast. It has many stars within it. Each of those stars probably has a solar system, or maybe an early solar system where planets haven't formed yet. Maybe it's just a ring of dust. Almost like there's a ring around Saturn, you can have a young star that has a giant ring around it, because none of the planets have actually formed yet. So the idea here is that the nebula is vast, much bigger than solar systems, much bigger than stars, and in fact is associated with the birth of stars. A galaxy, as we talked about, is an island of stars in space. It's held together by gravity. There are some other forces at play, such as dark matter, and it is orbited, well, of course, gravity actually acts on dark matter, but that's part of the story, and it's orbited at a common center. We think that most galaxies have supermassive black holes at their center. It's just a matter of whether that supermassive black hole is active or not, and that defines a quasar versus a more mature galaxy. But we'll talk about that in our chapter on galaxies. You can see there's kind of a common theme here. These are all things, this is introducing ideas that we'll have a whole chapter to get into. Okay, but again, galaxies are huge. They're unbelievably large. They're so much bigger than solar systems. 100 billion is such a big number. It's almost hard to comprehend. 100 billion is 1 followed by 11 zeros. That's how many stars, that's how many solar systems are in a galaxy. The universe is the sum total of all matter and energy, that is everything within and between all galaxies. And one of the great mysteries of the universe is it's not just galaxies and nebula, it's also dark matter and dark energy. In fact, dark energy makes up 60% of the universe, and we don't know what it is. And this is an idea we'll touch on, but since it's such a fundamental concept that's being studied currently, there's not too much that we can say other than that future generations will know more. So, when we look at objects that are far away, whether it's another galaxy or just a star that's far away within our own galaxy, we're looking back in time. Far away means back in time. This is an idea that I'll stress quite a bit throughout the semester, and you'll have some problems to practice understanding that idea. For example, when you look at the moon, you're actually seeing the moon 1 second before, because it takes 1 second for light to travel from the moon to us. That's not very long. Not much happens in a second. When you look at the sun, it's actually 8 minutes ago. So the sun could blow up and we wouldn't know for 8 minutes. Okay? Well, that would be bad and very unlikely. But You know, that's the idea. It actually takes time. Now here's some more dramatic numbers. Here's Sirius, a nearby star, actually quite close to us. It's 8 light years away. That means it takes light 8 years to travel from Sirius to us. So when we look at Sirius, we're looking back 8 years in time. When we look at our closest galaxy, now we're looking back 2.5 million years. So the galaxy that we see, the Andromeda galaxy that we see, this is how the galaxy looked when humans were first evolving 2.5 million years ago. Now we're looking way back in time. A lot could have happened in 2.5 million years. Even, you know, that's not that long in the age of stars. Stars usually have processes that take hundreds of millions or billions of years, but still, it's enough time. Things have changed. Things can change, right? And when we look at more distant galaxies, we're looking back billions of years, and now we're truly looking back on a cosmic scale. And we'll talk about the cosmic time scale in just a minute. When we see the Orion Nebula, we see the Orion Nebula as it looked 1,500 years ago, all right? And so good examples of this is when we talk about supernova and witnessing supernova within our own galaxy, nearby stars that are blowing up. That's something that happened maybe thousands of years ago, if it's a couple thousand light years away for that star, or hundreds of years ago if it's a couple hundred light years away to that star. Here we have an example. This photo shows the Andromeda Galaxy as it looked about 2.5 million years ago, right there. All right? When will we be able to see what it looks like now? Okay, make sure you can answer that question. When will we be able to see? How long will we have to wait to see the current Andromeda Galaxy? So you can think of the answer. All right, so let's make sure we're clear on the definition of a light year. Again, we'll get lots of practice with this. A light year is the distance. It's a distance, okay? It's not a time. I know the name makes it sound like it's a measurement of time, but it's not. It's a measurement of distance. It is the distance light can travel in 1 year, okay? Because light has a fixed speed. There's this one speed that light travels at in the vacuum of space, and that is it. Never goes any slower, never goes any faster. And it is, in fact, the fastest thing in the universe. It's the speed limit of the universe, the speed of light. Okay? A light year is about 10 trillion kilometers. Okay? Because the speed of light is about 300,000 kilometers per second. So then you just have to figure out how many seconds there are in a year, and that gives us our 10 trillion value. All right, kind of cool, okay? This is a lot of seconds in a year. Okay, so a light year, at great distance, we see objects as they were when the universe was much younger, as we were talking about. All right, here's the idea of the light year. There's that 300,000 kilometers per second. This is how many seconds there are in a year. Notice how we cancel out everything, and we're just left with kilometer, okay? All the units of time cancel out. 9,460,000,000,000 kilometers. That's how many kilometers there are in a light year. All right. Can we see the entire universe? All right. Well, no. Why can't we see a galaxy 15 billion light years away? Well, because the galaxy may exist at that distance, but light would be, because looking 15 billion light years away means looking to a time before the universe existed. Because it turns out that the Big Bang happened about 15 billion light years ago. Excuse me, made a mistake there. 15 billion years ago. So that means we can only look at things that are as old as the universe itself. There may be objects, in fact, we're almost sure there are objects further away because the universe has been expanding in all directions, but we can't see them because we're stuck looking back in time, right? It's like the very signal, the very thing that we see is a signal, and it takes time to move that signal from one place to another. We're limited. All right? And I'll let you think about the answers of other questions as we go through these quick checks in the slides, but I just wanted to kind of jump into that one. So, what have we learned? What is our place in the universe? Well, Earth is part of the solar system, which is part of the Milky Way Galaxy, and is a member of the local group of galaxies in the local supercluster. All right, and let me just see where we're at. Okay, so I want to see if we want to get to a good stopping point, or if we should just continue through. Excuse me for the interruption. All right. Right. So yeah, we'll stop at the next section. Split this into 2 videos. How big is Earth compared to our solar system? Okay. So let's reduce the solar system by a factor of 10 billion. The sun is now the size of a large grapefruit, 14 centimeter diameter. How big is Earth on this scale? What do you think? If the sun was a grapefruit, how big would Earth be? Think about your best guess here. Just kind of your intuition. How small is Earth compared to the sun? Okay? Ballpoint. Okay? So think about a ballpoint pin. So it's just that little metal ball at the tip of a ballpoint. okay, compared to a grapefruit. There's a lot of ballpoints that fit inside a grapefruit, thousands, right? So volume-wise, the sun is tens of thousands, hundreds of thousands, in fact, times bigger than the Earth, okay? On a 1 to 10 billion scale, the sun is the size of a large grapefruit. As we said, Earth is the size of a ballpoint, 15 meters away, all right? So 15 meters away, well, that's like 45 feet. So you got the grapefruit, and then you've got a little ballpoint 45 feet away. And all that's between, besides just emptiness, is Venus and Mercury. So we see the solar system is very much just empty space. On a 1 to 10 billion scale, it's just a few minutes walk to Pluto. How far would you have to walk to reach Alpha Centauri? Okay, so now I said, okay, so the solar system is mostly empty space, and we'd have to, take like, a half-hour walk to get to Pluto, right? So it'd be, like a kilometer away. But then how far is the nearest solar system? Is our solar systems close to each other? Well, turns out they're not. The nearest solar system would be on the other side of the United States. So the way I like to think about it, on this scale of the sun being the size of a grapefruit, the solar system is the size of a large college campus, like a park. And the nearest solar system, the nearest other star, is a park on the other side of the United States. And in between, 2,500 miles is just emptiness. That's why it's so difficult to imagine travel to other stars. It's difficult enough to send probes to the distant planets in our own solar system. We have to wait decades. If we wanted to travel to other stars, we'd have to travel for hundreds or thousands of years at our current technology level. All right? So we're a very long way off from being a civilization that spans multiple stars. It is a lofty goal. Is it possible? Yeah, technology changes dramatically, right? We've seen that already. But it would be a very different world where humans lived on different stars, okay, on more than one star, in more than one solar system. So how big is the Milky Way Galaxy? Well, the Milky Way, as I said, has about 100 billion stars. On the same 1 to 10 billion scale, how big is the Milky Way? All right, well, it'd be about the size of the solar system, right? It's that much bigger, all right? So suppose you tried to count the more than 100 billion stars in our galaxy at a rate of 1 per second. So you're like 1 star, 2 star, 3 star, 4 star. How long would it take you to count to 100 billion? Well, thousands of years. You wouldn't be able to in a single lifetime. You wouldn't be able to in many lifetimes, right? This goes to show what a big number 100 billion is. The Milky Way is about 100 billion, well, the Milky Way is one of about 100 billion galaxies, as I said. Oh my gosh, right? Every one of those is 100 billion stars. That means that we have 10 to the 11 stars per galaxy times 10 to the 11 galaxies. That means there are 10 to 22 stars. So there's 1 followed by 22 number of stars in the total universe. There are as many stars as grains of dry sand on all of Earth's beaches. Okay? That is an uncountable large number. Okay? This is a summary. I'd recommend you take a look at this, just summarizing the huge scale. I won't read all this, but it's a fun slide to read over. Okay, so here we'll wrap up video 1, covering section 1.1 from your textbook. And please check out the second lecture video where we'll discuss section 1.2 about the cosmic scale and the history of the universe itself, starting with the Big Bang. All right, thank you so much for watching.